Okay, thank you for having me. I appreciate the invitation to speak today. I'm going to change it up a little. It's been a great session so far, but I want to basically talk about what I consider to be a fundamental problem that a lot of people in this room are going to be facing very soon. And the basic idea here is that for quantum technologies, we have to sense single particles. And in the photonic side, we have to sense single photons. And so this is a real problem, and there have been lots of possible solutions to this, but I want to talk a little bit about the technology options and some of the commercial considerations. This is my outline here. So we'll just go through these things pretty quickly here, and I'll hopefully have some time for questions later. Before we get into that, though, I'll just give you a quick snapshot. My company, Anametric, we're a quantum photonic chip company. We've been building chips. Well, I've been building chips for 35 years, but starting at Apple back in the 80s. But we've been building chips for 6 years now, and we're on our fifth generation of quantum photonic chips. Our first market is in the cybersecurity space. So all this talk about PQC is definitely of great interest to us as well. We've had a lot of great supporters, and I would be remiss if I didn't mention the gentleman sitting right here, Mike Hayduck, who runs the information directorate at AFRL, and they've been great partners of ours, and we are very, very happy to have their support. We work closely with a group out of Southern Methodist University in Dallas, Texas, and specifically two professors there. One, Mitch Thornton, who is actually a quantum theorist, but he's also a cybersecurity expert. And the other is Duncan McFarlane, and he is an old hand in building photonic chips. So he's been building a high-speed quantum photonic chips for probably 30 years. Okay, so let's start with a little context. So why do we care about 1550 nanometers? And this is all basically about communication. So if you look at this graph here, this is an approximation of the attenuation or the transmission, depends on whether you flip it or not, of light through silicon fiber. And our entire world is wired up with this stuff. And so it bears a lot of attention on what's the frequency band that you really need to get the longest transmission length. And Andrew Shields talked about this earlier today. Really, there are two bands of interest. In fact, I think Andrew talked about the fact that they use both the C band and the O band. We basically have chosen to work at 1550. Now, if you say, oh, but all you're going to do is quantum computing in photonics on a chip, why do you care about this? And the answer is, well, as long as you're going to stay on chip, you probably don't. But the minute you have to combine multiple chips together to work together, and as we know, that's really the best path for scaling quantum computing, then you have to go off chip and you have to use fiber to connect them. So our attention has always been on the 1550 range, even though it would make a lot more sense for if we were going to stay on chip to go up into the 800, 900 nanometer range, because doing single photon sensing there is a lot easier. So anyway, it's all about communications. But here's the problem. Communications is an enormous market. This is a $24 billion market last year. And this is just for the photodetectors, not the communications market, just the photodetectors themselves. And estimated to be about $36 billion in 2027. Contrast that with how big the entire quantum computing and communications market is. And they don't even fit on the same scale. So you are here. If you're in the quantum business, this is definitely not a market driving economic situation. So that's why we have to pay attention, though, because that business, the global communications market, is the one that will have all the attention from the fabs. Okay, But there are other reasons to want to look at this near-infrared spectrum. And one that has happened to become a little more interesting over the last few years is temperature sensors. So these little thermometers that you've used on your kids or your parents, basically, that's a big and growing market. Also for surveillance, motion detectors, night vision goggles. That's this near infrared band is also quite a big market. About almost 4 billion in 2025 is an estimate. And then finally, probably one of the larger emerging markets is in transportation. So self-driving vehicles, they use LiDAR. And now I will say this though, those vehicles don't use only 1550 or near infrared because that's not really useful when there's fog or rain. So they use lots of different frequencies, but there are a large market, even in the 1550 range, estimated about 4.5 billion in 2029. So these are all really big numbers. And again, if you look at the entire quantum computing and sensing and communications market, it just doesn't move the needle compared to these kinds of economic headwinds. So let me take a slight break and talk a little bit about the technology, what's involved here. Excuse me, sorry. So basically, there are lots of different ways you can sense single photons. And these are really the two leading kinds of sensors that we have today. There are lots of others, but these are really what's driving the market. And the first is junction-based. So this is a very simple schematic of a photon coming in, hitting a photodiode, ejecting an electron into the conduction band, and creating an electron hole pair. And then we sense the output across that load resistor. The other one is, and you've heard about this as well here, is a superconducting nanowire single photon detector. Those are, and by the way, that image, I have to give whoever S. Kelly at NIST is credit because it's a beautiful image. I just had to use it. But the idea there is that you have a single photon that hits or is absorbed by this serpentine nanowire that is in the superconducting state. And you can really reliably sense single photons that way. The problem with that latter one is that it requires cryogenics. Until we get room temperature semiconductors, superconductors, that's going to be a kind of a problem. You certainly don't have room in your self-driving car for a cryostat, and most other kinds of things like your temperature sensor, you're really not going to need that. You're not going to have the power or the room for it. Excuse me, sorry. But so there are some fundamental physical things that you have to understand about this. At 1550 nanometers, a single photon has a little over 3/4 of an electron volt of energy. And so that's not a lot of energy. And if you basically eject a single electron from that, then you cannot sense it. It can't be done at room temperature, at least not directly. So what you have to do is you have to introduce gain. So when you create a single electron hole pair, then when you add gain, there are really two main ways of doing that. Inside the detector, you can actually have gain. Oh, thank you very much. Sorry. Yeah. So inside the detector itself, you can add gain by having single electron hole pairs, then create additional electron hole pairs. And excuse me. And once you've gotten there, then you can get somewhere between 200 and 1,000x gain. So a single electron hole pair or a single photon can create up to 1,000 electron hole pairs. Oh, sorry. And still, though, that's right on the hairy edge of being detectable. But then you can use inside the photodetector circuit, you can actually use external amplification or extrinsic gain. And in that case, you can basically generate 2 or 3 orders of magnitude a higher signal through that amplification. So there are other trade-offs you can make. One, by sacrificing efficiency, you can, excuse me, you can make the junction smaller, and that cuts down on the noise that's generated at that junction. And if you do that, then you can drop this down to your noise level down to the point where it's below this amplified signal. So 1 electron per second at, this is the amperage. It's 1.6 times 10 to the minus 19 amps, which is a really tiny number. You cannot sense that by a room temperature sensor. But if you multiply that by a factor of 10 to the 10, so now we're talking 10 gigabits per second of this sensor, then that is detectable. And I've actually built A to D converters that are able to sense in that range. So really what that means is maybe you can do it at room temperature if you just run your detection fast enough. So if you can count quickly enough, then maybe you actually can get there at room temperature without having to break the laws of physics. I'll just say at this point, I've built circuits. We've had 5 generations of chips that we have built over the last few years, and stay tuned. Okay, so now we have the knowledge that there's a physics-based way to get there, and we know we can build it in a lab. Question is, can we build it in a fab? Because building something in a fab is a lot harder than building it in a lab. And the problem with the fabs, as we said earlier, is that there's just no market in the quantum space that's big enough to get the attention of a fab. And so you have to make the business case for the fab that they really want to spend time and an extra effort to get your product off their line. So fabs, they basically are all about making money. They don't. There are a few test fabs, and we've been very lucky to have been partnered with one of those in Albany, New York, called AIM Photonics. But basically, they are there to make money. So what you have to do is you have to say, maybe there's a customer that needs this technology that the fab does care about. And that's why, if you go back to the previous slide, I talked about what are the different markets out there for these sensors in the near IR. That in fact, every one of those would like to have more sensitive detectors at room temperature and in much higher volume. If you remember back from Mr. Shields' talk earlier, one of the things that they have said, in order to make this worldwide quantum network a reality, you have to go to integration. You have to go to photonic ICs. And so the key to doing that is to get the attention of a fab. So that's the basic thing you have to know, is how to make the business case attractive to a fab. So I'm not going to mention who might possibly be the first to start, but there are people who are interested in exactly that. Okay. So basically, I'm just going to give a quick recap, and then there'll be a lot of time for questions. So near IR, the 1550 range matters. It matters to quite a few different application spaces, not just the quantum space. And in every one of those applications, though, room temperature is a must-have. So you can't go to one of those. You can't go to your autonomous vehicle driver and say, "Oh, I'm going to put a superconducting nanowire detector in the front of your fender." That's just not going to be a viable solution. So every one of those application spaces do demand room temperature. So it's not just a nice to have, although it's really nice to have for the quantum space. So the quantum community needs SPDs, single photon detectors. But it's not just in the communication space. As I mentioned, when you have multiple quantum computers, whether they're photonic or not, and they want to communicate with each other, the only solution is through fiber. I mean, you can try microwave conduits, but that's not really a highly scalable approach. This is a really tough technical challenge, and I know because I've been working on it for the last 6 years, but it's doable. There are lots of moving parts. But the key is to find somebody else who cares, who has a bigger pocketbook than you do. So that's really it. Let's be the the quantum tail that wags the fab dog, and let's move forward. All right. Thank you very much. Any questions?
Questions, please.
Scared them off.
Yep, here we go.
Yeah.
Here's one.
Yes. Right. Thank you. Great question. Yeah. So as you probably know, the superconducting nanowire detector efficiencies are in the 90+%, right? Junction-based detectors are nowhere near that. So when I mentioned in one of the earlier slides that you have to give something up in order to get to the point where a single photon at room temperature is practical, that something you have to give up is efficiency. And I'm not saying you can't get it back, because you can. There are different ways to do that. So you can have resonant chambers. You can have different kinds of reflectors into your system. You can have waveguides, which have the tapers that basically cut back on returned waves. Lots of ways that you can approach that, but you're still not going to get to the 90-95% efficiency range that you need for quantum computing, at least not soon. So yes, it's a great question, though. But by the way, these other applications, they don't really care. So communications, that's not their problem. Transmission efficiency is not the problem there. For quantum computing, absolutely, yes. But if you want to communicate between those quantum computers with the single conducting nanowire, you have to have that over fiber. So.